I know. There's a lot of things I teach that I don't necessarily love. But like my favorite classes were like the number theory classes. Like I thought number theory was really cool.
We don't really talk about this.
I know.
Yeah.
I know.
I guess you gotta.
Do you guys want me to teach you guys number theory?
Yeah.
Just like scrap the rest of it. Yeah. All right, so let's talk about where we were at. We're talking about antiderivatives. And remember, antiderivatives are really just like the reverse of finding the derivative. You know, if I gave you the derivative function and asked you to find where it came from, that's really what I'm asking you to find in terms of the antiderivative, okay? And we explored just using the y equals x squared, or f of x is equal to x squared, right? And we said the power rule basically is that if you kick up the power by 1, you got to divide by whatever that power was. That's the power rule. If you kick up the power, you got to divide by whatever that power was. So we said the antiderivative of x to the second would be x to the third divided by 3, or in other words, 1/3 x to the third, because that would eliminate that. Always remember that you have to have a plus c if I ask you for the general antiderivative, right? Because you could always have had a plus constant on the end, which when you take the derivative, it will cancel out. I have to give you some sort of information about the original function if I ask you to find what that constant is. I usually give you a coordinate or two to find it, okay? So, and then we just practiced, right? We just practiced more and more. Again, I would recommend if you want to print out that piece of paper, this is in the section 49 notes. This is a good kind of like reference sheet for you guys, just on antiderivatives. And yeah, we just practice. And then remember, this is kind of like what we did on the chapter, or the last chapter test that we had, the end of chapter 4 test, where I gave you a graph and asked you to know all of those important pieces. But now we're taking it one step further, and we actually graphed it beyond that. All right, so remember back when we started this section yesterday where I said, what if I had known the equation of some sort of velocity and I wanted to find position? You would be able to take the antiderivative of the velocity equation to find the position function, right? And if I had the acceleration function, you'd be able to work yourself backward to find velocity and work yourself backward again to find position, right? Because we know derivative of position is velocity, derivative of velocity is acceleration. So doing that is called, antidifferentiation is called rectilinear motion. Antidifferentiation is particularly useful in analyzing the motion of an object moving in a straight line. Recall that if the object has position function s, then the velocity is s prime, and the acceleration is then v prime, right? The velocity is s prime, and so the acceleration is v prime, so therefore acceleration is kind of like s double prime, right? We can use that to find, we can work ourselves backward, knowing that knowing the acceleration to work ourselves backward to find the position. So take for example this. Our particle moves in a straight line and has acceleration given by that function. We know that its initial velocity, which is something that you can usually calculate, you usually know. Initial velocity at any given at time 0 is -6 centimeters per second. And its initial displacement is 9 centimeters away. Okay. Find the position s of t. Find the position function. So this is kind of like the same thing that we did yesterday. We're finding the antiderivative of acceleration. The antiderivative of acceleration is velocity. So let's find the velocity. If a of t is equal to 6t plus 4, then v of t is the antiderivative of acceleration. Well, that would mean if the antiderivative is velocity, I got to kick up the power 1 divided by the exponent, and then attach a t to the 4. Right? Because it's like taking t to the 0, picking it up 1 to make it t to the first, dividing by 1. So it's really just attaching a t. And then what do I have to add on to the end? Plus a constant. So really our velocity is 3t squared plus 4t plus c. However, we know initial velocity. Initial velocity is -6 centimeters per second. So if v of 0 is -6, that means my c value is -6. Why is that? Well, just showing you here, if v of 0 is 3 times 0 squared plus 4 times 0 plus c, if that's -6, all of that is going to go away. Just leaving you with c is equal to -6. That's why c is equal to -6. So my general antiderivative function turns into my unique antiderivative of 3t squared plus 4t minus 6. There's my, oops, sorry, I shouldn't box that. That's not my final answer. Of course. 3t squared plus 4t minus 6. Because I wasn't asked to find velocity, I'm asked to find position, right? But we know the position is the antiderivative of velocity. So what we can say is position, S of t, is equal to, okay, do that process again, where you kick up the power and divide by the power. To each term, 4t squared now divided by 2. Attach a t onto the constant. And now, I hope you guys don't care. I'm going to use c again. I know I've already defined c to be something else. You can use d if you'd like. But it's plus another constant in the end. Okay, so S of t is going to be equal to t to the third plus 2t squared minus 6t plus my constant. But again, I'm given information. I know its original displacement was 9 centimeters. Its original displacement was 9 centimeters. S of 0 is 9. At time 0, it was 9 centimeters away. So that means that basically here, c is 9. For the same reason I used with my velocity, right? I hope we don't mind. I'm not going to plug in 0 and show that again, because all I'll do is just say c equals 9. All right, so now we have S of t is equal to t to the third plus 2t squared minus 6t plus 9. And that's my position. And using that, we could calculate where it would be at any given time. Okay? We knew the acceleration. We knew how much the acceleration was going to be changing. So therefore, I can then use that to find the velocity, and I can then use that to find the position, how far it is away at any given moment. Okay? If you know the velocity, or excuse me, if you know the acceleration, you can tell a lot. Right? You can tell velocity and its position, basically, by just taking the antiderivative. Okay, let's take a look here at this last one. Okay, a ball is thrown upward, straight upward with a speed of 48 feet per second. That's the original velocity. Not acceleration, but velocity. The original velocity, throwing it upward 48 feet per second from the edge of a cliff, which is 432 feet above the ground. So here's me. Okay. Okay. And my original velocity is 48 feet per second. And I know my original displacement is 432 feet. I'm not given any other information, but I want to know, find its height above the ground t seconds later. What is that really asking me for? Find the height above the ground. Find the height above the ground at t seconds. Position. It's asking me for position. When does it reach its maximum height? That's maximum. Then, when does it hit the ground? The zero of the position. Right? Okay, so let me ask you this. Does acceleration change on this ball? Does acceleration upward change? What changes though? Why is velocity changing? And gravity pulls it down, right? Isn't there an acceleration working on the ball? There's an acceleration working on the ball, pushing it downward, right? There's an acceleration. Does anybody remember what it is in feet per second? Feet per second. That's meters per second. I know. I don't know why they do feet per second. Negative 9.8 would be it. It's 32 feet per second. I know. Me too. And I don't know why anybody does. Negative 9.8 meters per second squared. It's negative 32 meters per second squared. That's the acceleration of gravity working on that ball. Now, you know what's cool? That's the only acceleration working on that ball. Okay. That is the only acceleration working on that ball. Yes? Oh, I'm sorry, feet per second squared. I'm sorry, yep. I forgot to change the label. And that's constant, right? Those numbers, negative 9.8 is probably the one that sticks in your head, but the negative 32 feet per second squared, that's the acceleration due to gravity pulling down on that ball at all times. Is the acceleration upward ever changing? Is there like a rocket strapped to the ball, pushing it further upward? I mean, maybe, but not in this situation, right? Okay, so what is velocity then? What's the antiderivative of acceleration? Negative 32 t plus constant. What's my constant? 48. I know my constant is 48. So I know v of t is really negative 32t plus 48. The first question asks me to find position, so let's keep going then. I'm going to use this equation here in a second, but s of t is going to be equal to negative 32t squared over 2 plus 48t plus a constant. Keep finding the antiderivative. So we know the constant again is 432. So s of t is equal to negative 16t squared plus 48t plus my constant of 432. Which makes sense. Like if I go back, this is so cool that we have this. If I go back to our quadratics chapter in Honors Algebra 2, we had this function. Negative 16t squared plus b sub ot plus h sub 0. That was what we used. You know what we could do to derive that? Take the antiderivative of the acceleration due to gravity, negative 32 feet per second. Isn't that what we have for our position? Negative 16t squared plus v sub 0t plus r h sub 0, original height. Isn't that cool? It's like coming full circle. I don't know. I thought it was so cool. Anyway, I digress. But that's our first answer. Find the height above the ground, t seconds. Then when does it reach its maximum height? Now, you know what I could do? I could find this one of two ways. I could take my position and find the maximum value. It's quadratic, so you can just take negative b over 2a. Is there a different way? Find the zero of the velocity. Yeah, I think didn't you say the critical point of the velocity, right? So really, let's do that. Because, I mean, we've done negative b over 2a forever. So let's just find the zero of the velocity, negative 32t plus 48 is equal to 0. So 48 is equal to 32t. We divide over, t is whatever 48 divided by 32 is. 1.5. Oh, that's why I did 2 times 32. 1.5. So the time, find its height above the ground at 2 seconds later, done. When does it reach its maximum height? Max height at 1.5 seconds. And then it wants to know, when does the ball reach the ground? Well, for that, I need to find the zeros of my position. All right, I need to find the zeros of my position. So let's just run quadratic formula, shall we? The opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we go inside our radical. 48 squared minus 4 times negative 16 times 432. And I square root that. 173.07. All divided by negative 32. Now, do I need to check negative 48? Yeah, I do need to check negative 48 divided by. Negative 48 minus 173.07 divided by negative 32, because this one's going to come out positive. 6.9. What I don't need to check is the other one. Look, negative 48 plus 173.07 divided by negative 32. Does that exist in our situation? Negative 3.9 seconds? No. So this is my only plausible answer, 6.9 seconds. To hit the ground. Isn't that cool? So cool. Just knowing the initial displacement and initial velocity. That's it. Cool. All right. I'm going to let you guys work on your homework for the rest of the class today. It's due tomorrow evening.